Have you ever wondered why the moon doesn't just fly off into space? Or how a car manages to turn a corner without skidding into oblivion? The answer lies in one of the most fundamental, yet often misunderstood concepts in physics. It's a force that dictates the very fabric of our universe. It's the silent architect behind every curve, every orbit, every thrilling loop-the-loop. Prepare to unlock the secrets of the force that keeps everything in line. At its core, centripetal force is the force that makes an object follow a curved path. Without it, objects would simply continue in a straight line. Think of it as the ultimate center-seeking force. The word centripetal itself comes from Latin, meaning center-seeking. It's always directed towards the center of the circular path. This direction is absolutely crucial to its function. This force is not a new, distinct type of force. Instead, it's a role that other familiar forces play. Gravity, tension, friction, or even the normal force can act as the centripetal force. Why is this force so vital? Because an object in motion naturally wants to continue in a straight line. This is Newton's first law of motion. To deviate from that straight path, a force must act upon it. For circular motion, that force must constantly pull it toward the center. Without this continuous pull, the object would instantly fly off tangent to the circle. It would escape its curved trajectory. Imagine swinging a ball on a string. The tension in the string is the centripetal force. If the string breaks, the ball doesn't magically continue in a circle. It shoots off in a straight line. Now let's clear up a common misconception. Many people confuse centripetal force with centrifugal force. Centrifugal force is often described as an outward force. However, it's not a true force acting on the object. It's an apparent force, an inertial effect. It's what you feel when you're in a rotating frame of reference. For example, when a car turns sharply, you feel pushed outwards. That's your body's inertia wanting to continue straight. The actual force keeping you in the car and the car turning is the centripetal force, acting inwards. Centripetal force is real and measurable. Centrifugal force is a fictitious force, an illusion of inertia. The magnitude of centripetal force depends on three key factors. These are the object's mass, its speed, and the radius of the circular path. The formula is elegant and powerful, F mv2r. Here, F is the centripetal force, m is the mass of the object. EV represents the object's tangential speed, and r is the radius of the circular path. Notice the V2 term. This means that speed has a squared effect on the required force. Doubling the speed quadruples the necessary centripetal force. This is why high-speed turns are so challenging. Conversely, a larger radius r means less force is needed. A tighter turn requires more force. Centripetal force is everywhere, silently orchestrating countless phenomena. Let's explore some dramatic examples. Consider a car taking a sharp turn. The friction between the tires and the road provides the necessary centripetal force. If there isn't enough friction, perhaps due to ice or excessive speed, the car will skid outwards. It loses its grip. Think about the planets orbiting the sun. What keeps Earth from hurtling into the vast emptiness of space? It's the gravitational pull of the sun. Gravity acts as the centripetal force, keeping our planet in its elliptical orbit. Without the sun's gravity, Earth would simply fly off in a straight line, a lonely wanderer. Another classic example is swinging a bucket of water over your head. The water stays in the bucket, defying gravity. The tension in your arm, transmitted through the bucket, provides the centripetal force. This force is greater than the force of gravity pulling the water down. It keeps the water pressed against the bottom of the bucket. Roller coasters are a thrilling testament to centripetal force. As you go through a loop, the normal force from the track pushes you inwards. This normal force acts as the centripetal force, keeping the coaster and you safely on the track. At the top of the loop, gravity also contributes to the centripetal force. It's a delicate balance. Even your washing machine uses centripetal force. During the spin cycle, the drum rotates rapidly. The walls of the drum exert an inward centripetal force on the clothes and water. The water, being less constrained, is forced out through the small holes in the drum. This effectively dries your clothes. Satellites orbiting Earth are another prime example. Just like planets around the sun, Earth's gravity provides the centripetal force. This keeps satellites in their designated orbits, allowing for communication, navigation, and weather monitoring. From the smallest atom to the largest galaxy, centripetal force is a fundamental principle. What happens if the centripetal force isn't strong enough? Disaster. If a car takes a turn too fast, the friction force might not be enough. The car will understeer, sliding off the road. If a satellite loses its orbital speed or encounters unexpected drag, it might fall out of orbit. It could re-enter the atmosphere. If the string holding a swinging object breaks, the object immediately flies off tangentially. It ceases its circular motion. This highlights the critical role of centripetal force. It's not just about making things turn, it's about controlling that turn. It's about maintaining stability and preventing objects from veering wildly off course. Understanding centripetal force is not just an academic exercise. It has profound implications for engineering, safety, and space exploration. Engineers design roads with banked curves to help cars maintain centripetal force, especially at higher speeds. Amusement park rides are meticulously designed to ensure sufficient centripetal force for safety and thrill. Astronauts and mission controllers must precisely calculate centripetal forces to keep spacecraft in orbit. From the microscopic world of electrons orbiting a nucleus to the cosmic dance of galaxies, this force is omnipresent. It's the invisible hand that guides motion in a curved universe. So, the next time you see a car turn or watch the moon in the night sky, remember the unsung hero. Remember the powerful center-seeking force that makes it all possible. Centripetal force, the silent guardian of every curve, every orbit, every spin. It's a testament to the elegant and dramatic laws that govern our physical world.